Now we're going to look at kind of combining the last two concepts here, what the inverse of a one-to-one function would be. So one-to-one functions, remember those are ones where everything here maps to just one thing. Same with going backwards, it only maps to one thing. So because of this property where everything maps to one thing both ways, we will know exactly what the inverse is, because whatever takes us here, which would be f, function f, the inverse will map us right back to where we started. So some examples here. We know f of 3 would be 7 because 3 maps to 7 here. So if we did the inverse at 7, kind of our result here, if we started here, we know we should map back then to 3 because that was our input here. That should be our result here if we do the inverse. And so all of these would end up being true, that the opposite ones would map here, because 1 maps to 5, the inverse would map back to 1, and the same with the last point. So what our result is that if you have something where we know that f at x, or sorry, yeah, f of x equals, well, f of x always equals y here, but if you do the inverse here, that means you're doing the opposite. So if we map backwards now, that means we should come back to our original result. So if f of x equals y, this is our input, this is our output. Okay, that means if you do the reverse, then if you start with y, you should end back with x. So if we start with y, the result should be x. This also means here, and kind of had this on a similar one, because y is the same as f of x, if you do the inverse of what you, the original function, you should get your starting value of x here as your output. What this also means is that the domains and ranges actually switch when you are looking at the inverse. So the domain of f becomes the range of the inverse. The range of the function becomes the domain of the inverse. So you flip-flop your domain and ranges when you look at an inverse. Let's do some examples here. So first here, they want us to find the domain and range of this function graph of f of x. So this is over here, this red graph is a picture of f of x. What's the domain and range? Let's start with domain here. Domain, that's our x values. Looks like it goes here from, let's kind of block in our axes just so we can see that a little bit better there. So there's our two axes. Looks like -1, -2, -3. Looks like it goes from -4 over to 3. And so our domain, we'll use boundary notation here, is -4 to 3, including those 2 points. What's our range? Our range, that's our y values. Looks like it goes from 0 on the bottom, is our y value, up to, if we look here, 2, 3, looks like it tops out at a y value of 4. Okay, so now what is the domain and range of the inverse? So if we're looking at the inverse, remember those are just going to flip-flop each other. So the domain of the inverse function here, f -1, would end up being the range of what we had before. So that's going to end up being 0, 4. The range of our inverse function would end up being the domain of our original one, so that would be -4 to 3. So they just switch when you want to find the inverse. Same graph. What is f at -4? So if we go over here, -4, is going to be this point right here. So it looks like negative 4 has a y value there right on the x-axis, so 0. What's f of 3? 2, 3. So if we follow it up here, and that's where it hits, looks like the y value ends up being 2, 3. Looks like y value ends up being 4. Okay, so now what about the inverse? So what would be the inverse if we started with 0? So now you're going the other way here. If we know from before that negative 4 mapped to 0, what are we going to do if we go back the other way? Where's 0 going to map to? Negative 4. So this would be negative 4. Same with the other one here. If 3 maps to 4, if we do the inverse, what's that going to map to? That should map back to 3. So you're going to get the opposite value if you do the inverse. Last thing here, because the inverse of f of a is b, if the function here at a maps to b, then the inverse of b is going to map it back to a. So because of that property, the graph of the inverses are always going to be reflections of each other across the line y equals x. Right here is that line y equals x. Remember that would be, it's kind of like x plus 0, so the y-intercept would be 0. Slope is 1 here, so we're going over 1, up 1, and so forth. So it's just like a 45-degree angle line right here, this line. The graph's going to be reflections across because, say for instance, we have the point 0, 1 on our, the functions on the other side. If we have on our function here the point negative 1, 0, that means f at negative 1 maps to 0. Negative 1 is going to go to 0. Then if we do the inverse, 0 is going to map to negative 1. That means f at 0 will give us the point negative 1. So that's the point, 0, negative 1. That's why that's going to have to be part of the inverse. Those points, those 2 points, and you could do it for anything, are always going to be across, like reflections of each other across the line y equals x. So that's just kind of a unique property about inverses when you graph a function and its inverse.